Imagine light, the stuff that lets us see. Pure energy, we think. Now, picture it acting like a solid block you could almost touch. But it still flows like water. Perfectly. Sounds like pure science fiction, right?
It really does. But believe it or not, physicists have actually, well, done it. They've turned that fiction into reality.
And that's exactly what we're getting into today.
Yeah, this is our deep dive into a pretty mind-bending discovery. We're looking at an Earth.com piece covering it titled, Physicists Convert Light into a Supersolid That Flows Like a Liquid.
Okay, so our mission here, for you listening, is to unpack this. It's complex science, for sure, but we want to make it clear, maybe even exciting, and show you why this seemingly abstract stuff could actually matter in the real world.
Right. The Earth.com article is basically reporting on a major paper that came out in Nature, the science journal. So it's legit, cutting-edge physics.
Okay. Light, solid, liquid, all at once. My brain's already hurting a little bit.
Yeah, it definitely challenges how we normally think about things. We usually picture light as waves, right? Like ripples on a pond or radio waves.
Sure.
But down at the quantum level, things get weirder. Light also acts like particles. Tiny packets of energy called photons.
Okay, the wave-particle duality thing. Got it.
Exactly. But here's the twist. These photons, they don't always just fly solo. They can interact with matter, with the material they're passing through in really specific ways. And when they do that, they can form these hybrid things. We call them quasi-particles.
Quasi-particles.
Oh, yeah.
So not just photons anymore. It's like a team-up.
Precisely. A photon plus some excitation in the material, it's this combined entity, this quasi-particle, that starts showing really unusual behavior.
And that leads us to supersolids, which sounds, I don't know, like an upgrade.
Yeah.
Supersolid Maker 5000.
Maybe. But yeah, a supersolid is a genuine, though very strange state of matter. Think about a normal solid, like ice.
Okay. Rigid structure, atoms locked in place.
Right, a crystal lattice. Orderly. That's one part of a supersolid. It has that rigid, ordered structure, like a solid. But at the same time, it can flow without any friction. None at all, like a superfluid.
A superfluid.
Yeah.
That's a liquid with zero viscosity, right? Flows without any resistance.
Exactly. Imagine honey that could just climb up the walls of the jar by itself because there's no internal friction holding it back. That's superfluidity.
Wow. So a supersolid has the structure of a solid and the frictionless flow of a superfluid. How is that even possible?
Well, that's the quantum weirdness. And the big news here is doing it with light, or rather, these light matter quasi-particles.
Right. The article mentioned previous supersolids were made from, like, supercooled atoms, gases.
Yeah, Bose-Einstein condensates of ultra-cold atoms. Extremely difficult, very specific conditions. This new experiment uses light interacting with a semiconductor. It's a totally different approach.
And the lead researcher, Dimitrios Trepidorgos, he basically said,
His quote was pretty direct. We actually made light into a solid. That's pretty awesome.
yeah, you can't argue with that. Making light solid is pretty awesome.
It really opens up a whole new angle on studying these states of matter.
Okay, so how do they actually do it? Make light solid? I mean, what was the setup?
Well, the details are obviously very technical, but the core idea involved using a special semiconductor device. It had layers designed to trap light, essentially.
Trap it like in a box.
Sort of, but more like confining it between mirrors and making the photons interact really strongly with the electrons in the semiconductor material. This interaction forms those quasi-particles we talked about specifically, things called polaritons in this case.
Polaritons. Okay, the light matter team up.
Right. And under the right conditions, specific temperatures, laser light intensity, these polaritons can form a condensate. That's a quantum state where lots of particles act like one single entity. And within that condensate, they found the polaritons arrange themselves into a regular grid, like atoms in a solid.
Ah, okay, so that's the solid part, the grid structure.
Exactly. But, and this is the kicker, measurements showed that this condensate, this grid, could still flow with zero viscosity.
The superfluid part.
Wow.
So it really is both at the same time.
That's the defining feature. Solid structure, frictionless flow. That's your light-based supersolid.
Okay, I think I'm starting to wrap my head around the what and how, but the big question is why? Why is this a big deal? What can you do with solid light that flows?
Right, the implications. Well, that zero viscosity property, frictionless flow, that's incredibly interesting for technology.
How so?
Think about anything where you want to move energy or information without losing any of it to, well, resistance or friction.
Like superconductors. for electricity.
Perfect analogy. Superconductors let electricity flow with zero resistance, which is revolutionary for magnets, power transmission, things like that. This frictionless flow of light matter particles could potentially do something similar in optical systems or even quantum computing.
Quantum computing, how would it help there? Those things seem incredibly delicate.
They are. Quantum states, qubits, are super fragile. They lose their information easily if they're disturbed or lose energy. A system where information carriers, maybe based on these polaritons, can move around without losing energy due to friction, that could lead to more stable, more robust quantum processors, less error-prone.
Okay, that makes sense. Less energy loss, more stability for those finicky quantum bits. The article also mentioned this helps study quantum physics itself.
Oh, absolutely. It's like having a brand new laboratory playground. You've created this exotic state of matter using light, so now you can poke it, prod it, see how it behaves.
What happens if you change the temperature or apply a magnetic field?
Exactly those kinds of questions. It lets us test the fundamental rules of quantum mechanics in a new regime. There was another quote in the piece from Alberto Bermati.
Right, from Sorbonne University.
Yeah, he said something like, while the team definitely made a supersolid, we still need more experiments to fully understand its properties. And further tests might reveal even more surprises about the nature of quantum fluids.
So, more weirdness potentially waiting to be discovered.
That's usually how it works in fundamental physics. You open one door and find 3 more you didn't even know existed.
The article compared it to superfluids, didn't it? How they were just a scientific curiosity at first.
Good point. Liquid helium flowing without friction was just bizarre when first discovered. A lab curiosity. But understanding superfluids led to advances in cryogenics, making things super cold, and developing incredibly sensitive detectors like squeeways used in medical imaging.
So this light, super solid, maybe it seems abstract now, but down the road.
It could be the basis for new kinds of optical devices, maybe for ultra-efficient information processing or storage. We're really just scratching the surface of what might be possible.
It sounds incredibly promising, but it also sounds difficult. Are there major hurdles, challenges they need to overcome?
Oh, definitely. As we touched on, creating these conditions is hard. You need very specific temperatures, laser properties, high-quality materials.
Right, keeping it stable must be tough.
Exactly. Maintaining that delicate supersolid state for long enough to really study it in detail or to use it in a device, that's likely a big technical challenge right now.
You need stability to see how it reacts to things, right? Like how flexible is it? What happens if you poke it?
Precisely. How does it respond to disturbances? Can it heal itself? These are key properties you need to understand, and that requires keeping it stable for longer observation times.
And are there still big, unanswered questions about the physics itself?
For sure. This experiment used one specific type of light-matter interaction, one type of quasi-particle. Could other types work? Could you mix different kinds of particles with light to get even stranger states?
Maybe entirely new phases of matter we haven't even predicted yet.
It's possible. That's the exciting part of experimental physics like this. You build something new, and you might find something completely unexpected.
It really just hammers home how counterintuitive the quantum world is, doesn't it? Things being solid and liquid at the same time.
It really does. It forces us to update our classical intuitions about what matter is and what it can do. It's all about these quantum rules allowing properties we thought were mutually exclusive to coexist.
Okay, so let's try and wrap this up. We've taken a deep dive into this, frankly, amazing discovery where light was coaxed into becoming a super solid.
Yeah, a state that's somehow both rigidly ordered like a solid, but flows perfectly without friction like a superfluid.
And this wasn't just a theoretical idea. They actually built it in the lab using photons interacting with the semiconductor.
Right, creating these light matter quasi-particles called polaritons, which then formed an ordered yet frictionless condensate.
The big takeaways seem to be, 1, it's a major advance in fundamental physics, giving us a new way to study these weird quantum states.
And 2, that frictionless flow property has some really exciting potential down the line, maybe for things like quantum computing or super efficient optical devices.
Even though there are still big challenges in, stabilizing it and fully understanding it.
Definitely. It's early days, but incredibly promising.
This whole idea, flowing like a liquid, yet structured like a solid main, it really shows how quantum mechanics just bends the rules we're used to.
It makes you wonder, doesn't it? What other fundamental lines are just waiting to be blurred?
Absolutely. Well, this has been a fascinating look into the quantum world. If you found this deep dive interesting, and maybe slightly mind-bending,
Which it definitely was.
then please do give us a like, subscribe if you haven't already, and maybe drop a comment below. Let us know what other science topics you'd like us to tackle.
Yeah, we'd love to hear your suggestions.
And hey, if you're really intrigued by quantum physics after this and want to learn more, we'll put some links in the show notes, maybe some good introductory books or online courses.
Just so you know, those will be affiliate links, which means if you happen to buy something through them, we might get a small commission, but it won't cost you anything extra.
Right, and it helps us keep making these deep dives for you.
So, thanks for tuning in.
Join us next time as we explore another intriguing subject. Until then, keep asking questions.
And keep learning.